It is. That's where we are right now. There we go. Wait. Okay, I got it. Whew. All right. That's where we are. Friction. I don't actually know what terminal velocity. Let's do terminal velocity. I forgot about that. A quick one on terminal velocity, just to kind of describe what it is and give you an indication what it is. But, okay. It was a myth. Or there's a saying that goes, and I heard this when I was a kid. If you take a penny, drop it off the Empire State Building, hit somebody on the head, kill them. Split their skull open, blood everywhere, just dead. No, actually no. And the Mythbusters actually did that in one of their episodes, and we all know we can trust the Mythbusters, okay? You don't have to believe me. I am some, guy. But trust the Mythbusters. They did it. No, you can't. And why is that? I mean, if we do the calculation for it, we can actually figure out how fast that penny or anything that we drop off the Empire State Building should be going by the time it hits the ground. We can do that. It's not hard. It's just rudimentary kinematic stuff that we did in the last unit. But what happens is it never ends up going as fast as the calculation says, because you run into air. All right, you remember that guy, Aristotle? Yeah, Aristotle. Socrates, Plato, the philosophizers. I think I've mentioned them before. If we take a piece of paper and a marker, and we drop them, well, you know what's going to happen. The piece of paper is not going to hit the ground same time the marker, even though I like to say gravity doesn't discriminate. Gravity doesn't care who you are, where you're from, what you like to eat, what your favorite TV show is, and what awesome shirt you like to wear. It doesn't care. Gravity doesn't care. Well, then why don't they both fall at 9.8 meters per second squared? Well, you know the answer to that. The piece of paper has surface area, and that runs into more air resistance than the marker will. So, was Aristotle right? Do lighter objects fall slower than heavier objects? Yes and no. Yes, if it gets in the way and we run into this air resistance thing. No, if you're on the moon. It wouldn't matter. Actually, they did that. Apollo, I think it was Apollo 15, one of the astronauts, and you can go ahead and YouTube it, Apollo 15. Maybe I should load one in there for you. YouTube it. They took a feather and a hammer and just went boom and filmed it, and then boom, they both hit the ground at the same time. And they fell slower because the gravity on the moon is not 9.8, it's only 1.62, so it is slower, it's 1/6. So it took 6 times longer for them to fall. But they hit the ground at the same time. There's no air, there's no atmosphere. There's gravity, but there's no atmosphere. So when you have atmosphere, then, okay, we'll draw this out for you. Let's say I got a rock. You're Charlie Brown going trick-or-treating. I got a rock. Who would give the kid a rock? I mean, really? And here are air particles. Okay, we'll draw some dots in here representing some oxygen, nitrogen, carbon dioxide, whatever. And so imagine this is falling through the air. Well, the object is going to hit those particles. It's going to hit those. And when it hits those, even though they're small, they have mass, and therefore mass and something accelerating into them is going to cause a force. It doesn't matter if you were... Okay, so you're driving down the road at 60 miles an hour, and you hit a tree. That's a bad day for you. Trees win, bad day. Point is, there's going to be a lot of force applied to your automobile and you. Now, what if it's the other way around? What if you're sitting there minding your own business, kind of hanging out, chilling? Okay, that's chilling. And the tree is running down the road at 60 miles an hour and runs into you. Whoa, am I doing hallucinatory drugs? No, just stick with me. Okay, so imagine a tree running down the road 60 miles an hour hits your car. How's that going to work out for you? Just as bad. No worse, no less. It doesn't matter who's moving. If the tree's moving and running at you, or you're moving and running at the tree, it's still a collision. The impact velocity is the same between the two things. It's going to be a bad day for you. Again, the tree would win. Now, the reason I said that is because these molecules aren't moving, but the object is falling through them, therefore causing collisions. And every molecule that it hits is going to apply a force, an upwards force, to the object that's falling. And what's that upwards force going to do? Let's just do a little bit of a vector. Oh, I know that nasty V word, but we have to talk about it. It doesn't go away. Vectors don't go away. So every time you have a collision, there's an upwards force in each particle that you're colliding with. And look, that's in the opposite direction of the force pulling it down. So if the force pulling it down, gravity, is being counteracted by force because of the collisions going up, then those are opposite vectors. They do subtract from each other. So it is possible for something to fall toward the Earth and get to a point where it falls fast enough. Now, if it's the faster it falls, okay, this is important as well. The faster it falls, the more particles per unit of time it's intersecting and hitting. So the faster it's falling, the more force is applied in the upwards direction. So it is possible to go so fast through the air, and there's so much upwards force because you're colliding with so many particles per second, that you can have enough force to counterbalance the force pulling it down. And those two forces can become equal. So when the downwards pull of gravity, okay, I'll put that as Fg, on my rock, okay, has been balanced by the upwards force of collisions due to air. Okay, that's the force, upward collisions due to air. Whatever. Call it force Bob if you want, or force up. Okay, that might be good. Call it whatever you want. It's America. Do what you want. Now, if these two things are balanced, the rock's not going to accelerate. Now, be careful. We didn't say the rock is going to stop. No, that's crazy talk. You drop something, it's not going to stop and just hover. It's not going to do that. If it did that, it'd probably be aliens. That's what I always blame. Blame aliens if something weird happens. And it happens to me all the time. There's a lot of aliens around, people. A lot of aliens. Now, that doesn't mean it's going to stop. No, it just means it won't accelerate anymore. Remember, I just realized I erased that. What the? What was I thinking? Last problem, I just took it all down. I said I was going to be up there forever. No. All right. Remember, in order to get an acceleration, you need a net overall force. That means you need something making it move to be greater than something, a force holding it back. And that gives me an acceleration. So if the two forces are equal, gravity pulling down and the force holding it back because of the collisions, then you're not going to have an acceleration. You'll fall, you're just going to fall at a constant rate. That constant rate fall, that overall constant, steady rate of fall, due to the air getting in the way, is called terminal velocity. That's what terminal velocity is all about, Charlie Brown. All right, so actually it's kind of interesting. This is kind of interesting. If you were high enough in the atmosphere, and going back, Felix Baumgartner, it's one of those names you just kind of never forget. Felix Baumgartner. And you know what I'm talking about? Red Bull guy, yeah, he went on top of that balloon, took him up 127,000 feet. I think it was about 127,000 feet. He set multiple records for this jump, and he just went pooh, and fell out of this balloon capsule and fell to Earth. He actually broke the speed of sound. He started going so fast, flying. Then he started encountering more and more atmosphere. But at 127,000 feet, most of the atmosphere is gone. Not all of it, but most of it's gone. So he starts encountering all of this air resistance. He started to slow down. He actually was going, if I remember the video correct, you check it out, YouTube it, Red Bull Felix thing, and you will find it's a cool video. They have one GoPro where you had a helmet cam on. It was a cool video. You gotta watch it. Cool. He was going 800 miles an hour or something like that, but then he started encountering so much air, he started slowing down. Imagine it, slowing down as you're falling, because you start hitting so much air that the upwards force is so great because you're going so fast that you start slowing down. Now, the terminal velocity for a human, a person who's just kind of tumbling through the air, is about 120 miles an hour, maybe 121, 122 miles per hour. That's still pretty fast. I mean, you hit the ground with 122 miles an hour. It's like hitting a brick wall, running into it at 122 miles an hour. Imagine that. No, don't try that at home. Do not try that at home, people. Okay? Trust the professionals. That's a bad day for you. So that's terminal velocity. Now, what if you have something, though, that's very light? Well, say we have a piece of styrofoam and a piece of lead. PB for lead, and I'll just put S for STY. We don't want you to think it's on the periodic table. It's not. Okay. Styrofoam, and they're same volume. They don't have, clearly not going to have the same mass. Drop them, go. Let them fall off the Empire State Building. Well, what happens? The same volume, so the same surface area, but this one's much less massive, much less heavy, weighs so much less that it doesn't have to go very fast to encounter enough air particles to reach its terminal velocity really quick. Back to Aristotle, was he right? Do lighter objects fall slower than heavier objects? Yeah, if you include air resistance, he was correct. Now, of course, when we talk about it in physics, we 99 out of 100 times say disregard air resistance. Now, we can put it in there. We'll do a problem later on when we do put air resistance in, but for the most part, we disregard it. So things can only fall so fast, and let's go back to the penny. The penny's not going to kill you. It has a surface area as it's tumbling. It's flat. Reaches around, if I remember my Mythbusters correct, about 56 miles per hour. If it hits you on the edge at 56 miles per hour, it could probably put a dent in your little skull there and bleed, but it's certainly not going to kill you. All right, so ants, A-N-T-S, okay, not the A-U-N-T, those are your auntie. No, this is, the little things that crawl around and they like crawl around the lanes. You know, what I like to do is, when they're crawling across like a table, I like to go, boom, flick them. Just go, boom, flick them. Don't kill them. Just, boom, flick them. Unless they're in the house, then I kill them. Sorry, kill them. Flick. What's kind of cool, they'll just fall off that table, and they'll hit the ground, and just walk away, laugh at you. Yeah, dude, you got nothing, okay? I'm an ant, okay? A table to an ant is equivalent to about, 20-story building. You fall out of a 20-story building and see if you get up and walk away. Don't do that. I'm not suggesting that you do that, okay? Please don't do that. You do that, I'm going to get in trouble. I'm going to say it was my fault. An ant, boom. Why? Because the ant is relatively light. They're wicked strong. They can lift 50 times their own weight. Just don't mess with an ant. And they have a decent amount of surface area compared to how much they weigh. So their terminal velocity is reached almost immediately. Okay. Interesting fun fact, little quick story for you. Let's make sure I covered this. So if we go, okay, so a heavier object is going to have to go a lot faster to encounter enough air particles to hold it up and therefore counteract the force of gravity pulling it down. So this will have a much higher than this one, terminal velocity. There was a World War II story. You can look this up as well. Just type in World War II, British bomber guy survives fall. You'll find it. And it was interesting. He was in a bombing raid over Germany, World War II, at night. He was the tail gunner. Bomber got hit by anti-aircraft fire. Fuselage starts on fire. Pilot gives the order to bail out. He gets out. His parachute's on fire. He's at 20-something thousand feet with oxygen. At 20-something thousand feet, you need oxygen unless you're acclimated to it, which he wasn't. He flew up there and never flying down. So he's like, all right, this is it. I don't want to go in a fiery plane. So what does he do? He can jump out of the plane. I don't remember where. And he just pulls oxygen mask off and pass out. And that's it. Game over. Right? This is what he does. Wakes up in a German POW camp with a Gestapo agent pointing a gun at him and asking him questions, threatening to shoot him because he's a spy. He goes, dude, I'm not a spy. I was in a bombing raid last night. I jumped out of the plane, and here I am. I don't know what happened. And the Gestapo agent, well, where's your jacket? You're out of uniform. Because according to the Geneva Convention, if you're out of uniform, you can be shot as a spy. Spies can be shot legally. So we convinced the Gestapo agent enough to at least investigate his story. So we took him, the bomber guy, who, by the way, was in bad shape. I mean, he had a broken hip. He had broken bones, but he was alive. And they made him walk to where they found him, or actually where he was turned in by a German farmer. And it was in winter. if I remember right, it was in the Black Forest of Germany. It was in the wintertime. And they saw why he lived, how come he lived. Apparently what happened was he had fallen and he hit a pine tree, which is covered in snow, bounced off the pine tree, hit the side of a barn, okay, this is angled now, and then was just covered in snow and landed in a soft hay area, which were covered in snow as well. Talk about lucky. So remember, it ain't over until it's over. Oh, by the way, so they believed him. And they found his flight jacket, his nice flight jacket, heavy, warm flight jacket. The farmer took it off of him. Okay, I mean, kind of can't blame the guy. All right, so that was kind of a story. If you've actually listened to this video this long, well, congratulations, good for you. That's just talk about terminal velocity and force pulling down. Again, we're not going to do a calculation with that one yet, but we will get to the terminal velocity calculation. Just wanted to let you know that, to introduce it as a topic.